We're going to switch gears, I think, and go back to talking about star forming, more distant star forming galaxies.
Good afternoon, everyone. Today I'd like to talk about dusty star forming galaxies. These galaxies produce lots of UV photons, but 90% of the photons are absorbed by dust and re-emitted in far infrared. And because the far infrared is really long wavelength, it's really difficult to resolve these galaxies. So today I'm going to talk about how we learn about star formation rate from resolved versus unresolved dusty star forming galaxies. And first, just a quick reminder of the property of dusty star forming galaxies. This is the spectral energy distribution of a dusty star forming galaxy. And it's approximately a black body, and you can see that the black body is the peak is at about 100 micron, or 3,000 gigahertz. And we almost always work at the Rayleigh-Jeans tail. That's this part, That's this part of a spectrum. And you might have heard the so-called negative K correction. Basically means that if we go to higher redshift, we effectively go to shorter reference wavelength. So we climb up this Rayleigh-Jeans tail, and so that the galaxy actually doesn't appear much fainter than low redshift. That's why we can observe these galaxies even at very high redshift. And so if we observe, most of the time we actually don't resolve these dusty galaxies. And if they are unresolved, then we just get those far IR photons, and they appear like a far infrared background. And the idea is similar to what Tony Lee talked about earlier we basically have an intensity of these far UV photons. And it's first discovered with Kobe CMB experiments, and of course we don't know where these photons come from, or we don't know the information of those galaxies. But if we have large telescopes, we can resolve them, and then we often call them submillimeter galaxies. And actually, far infrared and submillimeter usually means the same thing. And it's first discovered by SCUBA. And if we have a statistical sample, we can measure the correlation function and recover the halo mass of these galaxies. So the first part of this talk, I will talk about cosmic far infrared background. Oh, by the way, you might have heard of cosmic near infrared background. Those actually come from old stars rather than dust. Today I'm talking about far infrared. Those are from dust. And the two questions I'd like to address is, how well can CIB constrain star formation history, and what is the optimal design for future experiments? So I'm going to apply the halo model and the principal component analysis approach to address this question. So first, as I said, that the CIB is basically unresolved far infrared photons, so we measure the intensity and also the power spectrum. So here is an example of the CIB power spectrum measured by Planck, the angular power spectrum CL. And you can see that most of the signal is between L100 to 1000. And since Planck has so many wavebands, we can measure the auto and cross power between these different bands. And at 217 gigahertz, it's dominated by C and B. And at 3000 gigahertz, it's actually dominated by galactic dust. So this is roughly the frequency or wavelength range that we can observe. This is 100 micron, and this is about 1500 micron. So I like to model this power spectrum. And the approach I use is the halo model. And of course, we need the IR luminosity as a function of halo mass. And here I'm showing one example, actually two examples of IR luminosity function as a function of halo mass. And this dashed line is the one I took from the Planck paper. And here I'm also showing one model from Peter Baruzzi, the star formation rate versus halo mass. And I'm assuming that IR luminosity is proportional to star formation rate, and with this Koenig factor K. And actually the results, and I found that the results actually depends on how you parameterize the IR halo mass relation. So I did more parameterization with more degrees of freedom, the so-called piecewise continuous parameterization. I have bands of halo mass, and for each mass band, I have a free parameter describing the IR luminosity in that band, and I also do this for redshift bands. And with this, I can see how well can the power spectrum constrain these parameters. And the result is the model plot, the star formation rate per volume as a function of redshift. And let's first look at this purple curve is the one from Brent Robertson's recent paper using optical and updated optical depth. And this orange curve is the one published by Planck, actually. So it seems like the CIB is constraining or is predicting or is telling us that there are much more star formation rate than observed by optical. But then I redid the constraints using the piecewise continuous parameterization, and I found that actually at most constraints actually is below redshift 3. And above redshift 3, you can actually don't get enough, you don't get very much constraints there. Basically, yes. And with my piecewise parameterization, I can perform principal component analysis to see actually where the signals are. So here's my 5 bands in mass and 5 bands in redshift, and then I calculated the feature matrix and calculate the eigenvectors, or basically the principal components. So the first principal components indicate the modes that's best constrained. So you can see that the peak is at low redshift 0 to 1, and halo mass 12.5. And it's not surprising, this is the one with highest star formation rate. And then the second principal component says that the second best constrained modes is the difference between this and this. And the third PC has 3 components, and so on. So with this tool, I can assess what the constraining power for a given CIB experiment design. So I talked to people designing future CMB experiments. They always have, so like CMB experiments beyond Planck, they tend to have lots of wavebands, or good angular resolution. It's often a trade-off between the number of bands versus angular resolution. So from the CIB perspective, if we want to constrain star formation rate, what is the optimal combination of the two? So this figure, the x-axis shows the angular resolution, and y-axis shows the number of frequency bands. And the color coding is the mode that can be constrained. So if we have very high resolution and lots of frequencies, of course, we can constrain everything. But if we have not very good resolution, like say 20 arc minute, and we actually don't get much constraints on star formation rate, this makes sense because for power spectrum, we like to go to smaller scales to have more modes. And this is actually similar to the design of PIXI, which is currently optimized for CMB rather than star formation rate. So yeah, the one quick answer is that we like to have at least 20 arc minute resolution and 20 bands to have good constraints on star formation rate. And the final part of my talk, I'll be talking about submillimeter galaxies and the science case of a new survey, and why do we need a new survey for submillimeter galaxies, and also how well can we recover halo mass from clustering to get the star formation rate as a function of halo mass. So this survey is called Schnittor Submillimeter Survey Telescope, or CSST. It's led by Sunil Gawala at Caltech. So the idea is that we know that ALMA can resolve submillimeter galaxies to like very good resolution, the things that we actually don't know or haven't discovered very many submillimeter galaxies. And the idea here is that we use one band, A50 micron, to survey a large area of the sky and to find those submillimeter galaxies. And then first, we can use that to constrain star formation rate, and we can also provide targets for ALMA. And also, these targets tend to be highly obscured so that we cannot find them in optical wavelength. And so the idea is that a 30-meter telescope and A50 micron as a survey band with 7 arcsecond resolution. And really large field of view, you can see the comparison between IRAM and LMT. And it's covering 1,000 square degree per year, roughly 10 to the 7 galaxies. And because of the negative correction I said earlier, that we can have a threshold that's almost constant, a star formation threshold that's almost constant, meaning that we are going to observe all galaxies with star formation rate greater than 100 solar mass per year. And by the time that this is service complete, we'll also have photos of these from LSST and Euclid that we can study those. We can have the redshift for these galaxies. And people at Caltech also working for the spectrometer for this survey. So my work is I'm working on a Mach catalog for such a survey. So I took the Bolshoi light cone 2 square degree provided by Peter Baruzzi, and then I painted some submillimeter properties on them based using Matthew Betterman's model. So here's one example, the number of galaxies as a function of the A50 micron flux threshold. And the design of CSST is, the confusion limit is about 0.7 millijansky, so it's around here. So we expect to see a few thousand galaxies per square degree. And the interesting part is the flux as a function of threshold. So you can see that it plateaus. So if we don't resolve anything, this is our CIB intensity. But if we resolve it down to 0.7 millijansky, we actually resolve about a quarter to a third of all the submillimeter galaxies. And we like to use. So once we have this sample, we can use the halo mass. We can recover the halo mass from measuring the correlation function. And this is a measurement I did with this Mach catalog. So again, the galaxies selected with this A50 micron flux threshold, and various curves shows the correlation function of the various halo mass bands. And I can use this method to recover the halo mass of these galaxies and to recover the star formation rate as a function of halo mass. And as I said, that we are most likely to have photometric redshift, which have quite some uncertainties. And here I'm showing how does the photometric redshift impact our measurement of angular correlation function. Here I'm just assigning a random photo Z or redshift uncertainties and just illustrating how photo Z's impact our angular correlation function. And I'm currently working on implementing more realistic photo Z's based on Cosmos, working with Peter HiPACC, and to have more realistic assessment of the impact of the photometric uncertainties. And to summarize, I've talked about the cosmic far infrared background and submillimeter and how they are complement to each other, and I talk about the optimal future CIB experiment design, and also talk about this CSST, which plan to survey lots of sky and find lots of these submillimeter galaxies. Thank you for your attention.
Start shouting.
Yeah, so I'd like to inquire a little bit about your star formation rates you would derive from such a survey. Now, Herschel has shown us that as you go down the luminosity function of the known submillimeter population, so that's slightly lower redshift, than what you're aiming for. As soon as you get away from the extreme outliers into the normal population, there are ranges of temperatures you would see, not just sort of single temperatures, such that there is no single correlation anymore of sort of scaling function of submillimeter flux to luminosity. And Herschel also has shown us that the dust temperature of galaxies varies, as a function of a number of parameters: stellar mass, position in the stellar mass star formation rate plane. So with a single or a narrow band observation in the submillimeter, and then perhaps not even having a redshift, how will you get accurate star formation rates?
Yeah, so there are definitely lots of assumptions in these models, or in the HALO model I talked about. And there we actually have very simplistic model, just a star formation rate as a function of mass. It's like, we definitely skip lots of the complexities in those models. And the things actually we are trying to answer is that with this several power spectrum, actually how much constraints can we actually have on the star formation rate? And we just want to adding one complexity at a time and see how much constraint we can actually get, and then try to have enough nuisance parameters so that we don't over constrain or have unrealistic constraints for the model.
Quick question regarding the last plot you showed, how the angular correlation function changes due to redshift errors, right?
Yes.
I'm very surprised that you see such a strong evolution. That sort of only makes sense to me if the actual angular correlation function itself would be a very strong function of redshift. Right? You're going to scatter things in and out of your redshift bin. So have you assumed that you're only scattering things out of your redshift bin but not into it? Is that what's
both
going on?
ways.
Then why is there such a strong dependence? Is there really a very strong redshift dependence in the angular correlation function?
So, let's see. It's almost a constant.
Oh, no, it's because they're not correlated anymore when you...
Sorry,
I think I understand.
I think I have answered. I'll find you here.
Any other questions while the next speaker is setting up? Okay. If not, then we